Hello class! This video is on calculations with heating curves part 1. We're going to introduce some vocabulary, go through the phases of a heating curve, and then overall we'll get to some math calculations and which equations we're going to use in each of those situations. Before we get to the math, we have to talk about some vocabulary. First vocabulary term is specific heat. We abbreviate it as a lowercase c. And this is the amount of heat needed to raise 1 gram of a substance 1 degree Celsius. Because we're looking at heat for every gram for every 1 degree Celsius, your unit would be heat, which is measured in joules, it's a capital J, for every 1 gram for every degree Celsius. So joules per gram degree Celsius is how I say that in class. Now, what does this term mean? Well, if we have two different substances, for example, 1 gram of metal and 1 gram of water. Let's look at our metal first. If this is at, 20 degrees Celsius, and I start heating this substance up. So I've got my little burner. That's a Bunsen burner. Beautiful picture, right? If I start heating this metal up, then all of this energy is going to be transferred into my metal. The amount of heat that it takes to go from 20 degrees Celsius up to 21 degrees Celsius, that is the specific heat. So if this metal was aluminum, for example, all of this heat transferred in order to go 1 degrees increase is only about 0.9 of a joule. That's all the heat that it takes to heat up this 1 gram of metal 1 degree Celsius. Now, if I transfer that into the specific heat of the metal, I would write it as 0.9 joules for every gram for 1 degree Celsius. And that is where our number for specific heat capacity comes from. Similar for water. If I was to heat up my water, well, water heats up a little differently. Kind of like if you've ever gone to McDonald's and you get those little apple pies. On the side, they have like, caution, the filling is hot. Well, it's not the crust that's hot, but it's the filling. And that's because different substances heat up differently. So if I take water, 1 gram of water, I heat it up. I have the same energy transferred in. I'm starting at 20 degrees Celsius and going to 21 degrees Celsius, a 1 temperature increase. Water is going to be really hard to heat up. It's going to take 4.18 joules in order to heat this much water by 1 degrees. A lot more energy than my little 0.9 number for my metal. So we say that this 4.18 is joules per gram degrees Celsius because I'm heating up 1 gram of water and I'm only heating at 1 degree Celsius. That is where my specific heat for liquid water comes from. And that number is going to show up again once we hit our calculations. All right, so that's your specific heat capacity. Other vocabulary that you'll need to know. Your heat of fusion, we abbreviate it as an HF. This is the amount of heat needed to melt a solid. Long story short, you're either melting or freezing and you're using heat of fusion. Now, let's dive a little deeper. When you have your solid, you have something called a lattice work. So you can also say that this is the amount of heat needed to break apart your solid's lattice work, pulling those particles further apart to become that liquid. For example, if I've got a solid here and a liquid, my particles of my solid are rigid, they're uniform, they're structured, they're just sitting there kind of vibrating, they're attracted, they're repelling, they're in a lattice structure. If you think of them on a spring, like being attracted and then repelling and attracted and repelling, and that back and forth vibration, kind of on two ends of a spring. Your heat of fusion is the amount of energy it takes to break that spring apart. So they're on the spring, enough energy, add enough energy, and boom, they're going to separating. So all these particles here are vibrating, they're vibrating, and then they'll start splitting apart. And when they split apart, they sink to the bottom, so they become a liquid. And we haven't lost any particles, they're just now spread out. They're taking up more space. They're no longer right next to each other, they're no longer attracted to each other. They're moving around freely with more space between them, further apart. Since all we're looking at is how many particles we have, this is the amount of heat for the amount of matter that we have, or the grams that we have. That is for solid to liquid. We also have another phase change where we take our liquid and then heat it up and turn it into a gas. That is called your heat of vaporization. We abbreviate it as a little HV. This is your amount of heat needed for your liquid particles to spread out more and become a gas. At one point in time, we had talked about how your liquid particles kind of pop out. So when your particles have enough energy, they break free of their liquid phase. So this is the amount of heat needed for particles to pop out of your liquid phase. And then they start moving around more freely. They've got more space between them, so they're becoming a gas. Kind of what that looks like is if here we have our liquid particles that we do up here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Same number of particles. We heat them up. They're like moving around, floating around, kind of like this. Keep heating them, and they're going to start moving around a lot faster and a lot more spread out. So these particles are going to kind of jump out of your liquid phase and then become a gas. So there's a lot more space between them. If you don't have a lid on your container, it's going to be easy for those gas particles to escape. 1, 2, 3, 4, 5, 6, 7, 8, 9. A lot more space between them. We're spreading out our particles because we're turning it from a liquid into a gas. Same idea, we're based on, for your unit, we've got our heat that it takes for every amount of mass that we have, so our gram, joules per gram. So some slight differences between the unit of all three of these values. Now, let's do a quick recap of your heating curve. So I've got I'm trying to put this whole thing under my document camera, there we go. So I've got temperature on my y-axis and energy on my x-axis, the amount of energy being supplied. And if I take a substance at a really low temperature, so let's start with solid, really low temperature, really cold ice, what's going to happen is it's slowly going to heat up. If I take a solid, pull it, start pulling it out of the freezer, it's a bad example. For example, let me move away from water for a moment. If you stick a piece of metal in the sunshine, it's going to heat up. It's going to stay as a solid, but you can have your solids be at different temperatures. So in the case for water, I can have water be really cold, and then, or my ice be really cold, and then you can have different temperatures for your ice cubes. You could be at negative 100 degrees Celsius, really cold, negative 10 degrees, negative 5 degrees, negative 1 degrees. Those are all really cold temperatures for your solid ice. Now, when we start heating this up, notice we are changing our temperature. Because we're changing our temperature, we're changing the speed at which our particles move. So anytime you have a temperature change, you're changing your thermal energy. So your temperature change is a change in your thermal energy, which means that your particles change their speed. So in this case, I've got particles moving at a different speed in my solid phase. for water. Once you reach 0 degrees Celsius, what starts happening is that these particles are no longer moving at different speeds. They start separating. They start pulling apart. They start getting further and further. We have enough energy that we have broken apart our lattice work. So it starts to flatline at 0 degrees Celsius because instead of speeding up your particles, we're now melting our solid, going from a solid into a liquid, and that process is because we're pulling apart the particles in my lattice work. I'm pulling them apart in order to move around and become a liquid. About here, we're at 100% liquid, so I can start heating up my liquid, heating up my liquid, heating up my liquid. It was at 0 degrees. I can go through 10, 20, 50, 70, all the way to what is known as my boiling point, which is 100 degrees Celsius for water. So once I hit 100 degrees Celsius, this is my liquid that I've been heating up. I start boiling. And the process for boiling is when I'm going from a liquid into a gas. And again, if I look back at this picture, it takes a certain amount of energy to do that. My particles have to spread out. They have to take a whole bunch of space. They have to pop out of this liquid phase. Because I'm spreading them out, it's going to flatline. I'm not changing the temperature. I'm instead changing my phase energy. So your phase energy is when you go through a change in your state of matter. And instead of speeding up your particles, we're now pulling them apart. Now, once you've evaporated all of your gas, once you've boiled off all of your gas, you've turned it into a vapor, you can have your gas phase be at different temperatures as well. So your gas can be at 100 degrees. If we stick it in a balloon, we could heat it up a little bit more, keep it contained, and we can take different measurements for gases at different temperatures. Okay, so that's the general idea behind your heating curve, where this is boiling or evaporating. And this is if you are adding heat. So again, we've got energy here on the bottom. This is a low amount of energy, whereas over here we have a high amount of energy. If I'm looking at a cooling curve, I'm instead removing energy. I don't have as much energy. I'd simply be going the opposite direction. So I might start with a high gas, move this direction and start condensing, take my gas into a liquid, start condensing. I can cool down my liquid, so instead of at 100 degrees, it's now at 0 degrees. I can stick it in the freezer, and instead of melting, it's going to be freezing, going from liquid to solid, and then I can cool that solid down more. So you can either read it left to right for a heating curve, or you can read this right to left for your cooling curve. That's a brief introduction into your vocabulary and your heating curve. I'm going to pause here and we'll get into our equations in our next video.